Welcome to all of you. This is the numerical analysis semester 6 under CCF paper DSCC 15 mathematics major. The fixed point and floating point representation. The syllabus on this chapter 1, representation of numbers and errors in numerical analysis, machine numbers, floating point and fixed point, sources of errors, rounding of numbers, absolute and relative error, significant digits, and error propagation in machine arithmetic operations, numerical algorithms, stability and convergence. Machine number representation. In numerical analysis, machine number representation refers to how real numbers are stored in a computer's finite memory. Since a computer cannot store an infinite number of digits, like pi is a rational number, infinite number of digits contains in pi, and 1 by 3 is also contains infinite digits 0.3333, and we use two system, fixed point and floating point. What do you mean by fixed point representation? Fixed point representation is a method of storing real numbers in a computer where the position of the radix point, that means binary or decimal point, is set at a fixed or predetermined location within the sequence of digits. This means a fixed number of bits are allocated for the integer part and a fixed number for the fractional part. The computer treats the number as an integer and the programmer implicitly handles the scaling factor and the location of the point. Fixed point means here that is the binary point or decimal point is fixed, predetermined. It is more clear by where the rightmost 8 bit for fractional part, this is the rightmost, this B0 to B7 8 bit, and the next 7 bit from B8 to B14 is the integer part, and the leftmost position, most significant bit, this is the leftmost position, this 1 bit, that is the position B15, is the sign bit. When number is positive number, then bit is 1, and when negative number, then sign bit is 0. In this place, 0. For positive number is 0, and for negative number, sign bit is 1. So this is the structure of a fixed point Q8.8 16-bit binary number. The advantages of fixed point iteration. In a fixed point system, a specific number of bits is reserved for the integer part and specific number for the fractional part. And the point, that means the binary point, never moves. And this point, binary point, fixed in this position. And the predictability, since the point is fixed, the resolutions, the smallest possible difference between two numbers is constant across the entire range. And the performance, that is the operations are generally faster and require less complex hardware in the computer. And the range very limited. It cannot represent extremely large or extremely small number effectively. So this is the resolution, the smallest possible difference. Next, represent the following decimal numbers in 16-bit Q8.8 fixed point binary form, 64.75 and minus 64.75. And this is the number, decimal number. We want to convert this decimal number to fixed point binary form. Obviously, this 64.75 is positive number, so sign bit is 0. Next, we convert this integer part 64 decimal part to binary, and division by 2, the remainder is 0, and this remainder 0. So from the lower to upper, this 1 0 0 0 to this is the binary representation of this integer 64 in decimal. Next, we convert this decimal part 0.75 to binary part. Multiply by 2, this 1.50, so integer is 1. And next, fraction part 0.50 multiply by 2, this 1 0, so integer is 1. And so this 0.75 in decimal converts to binary in this form, this 1 1, and the other places filled by zeros. This is the binary form of this decimal. So this 64.75 in decimal point converts to binary form. This is the 1 0 0, this 0 0 0, 0.11, and other places filled by zeros. The value of 64.75 in 16-bit signed magnitude fixed point binary representation is given by, so this number is positive number, so sign bit is 0, and integer part 7-bit, so integer part 7-bit is this 1 0 0, and next 4 zeros, this is the integer part, and this is the fractional part is the 8-bit and this. So combining all this, we write 64.75 in decimal equal to this is the fixed point 16-bit binary representation. Next, minus 64.75 in 16-bit fixed point binary form. We always use here 2's complement method for any negative number. When we convert decimal to fixed point binary, 16-bit Q8.8 fixed point binary, then we always use 2's complementary method, because there are many advantages for 2's complement method. Other methods are 1's complement method and so on, but we recommend here for 2's complement method. The corresponding positive number, first we find the corresponding positive number. Already we have find 64.75 is this fixed point sign magnitude form is this. Already we have find in the previous slide. So this is the 64.75. This is the 16-bit fixed point binary. Next, we find the 1's complement form, including the sign bit. That is interchanging 0 by 1 and 1 by 0. So this 0, so this is the 1, this 1, next place, this is the 0, and this 0, this 1, and so on, so on. Last, this is the rightmost place is 0, so this is 1, and so on. Next, we add 1 to the rightmost bit, that is least significant bit. This is the rightmost bit is this. This is the least significant bit. Add 1, and this is the 2's complement form. So 1 plus 1 is 0, and this carry 1. So 1 plus next one 0 carry 1. This 1 plus 1 0, this carry 1, and so on. And this is the 2's complement form of this. Next, now bitwise position of this number. Actually, this is the required answer. So bitwise form, this sign bit, this is last, this is the most significant bit, the leftmost bit 1 is sign bit, and next 7 0 1 1 and 1 1 1, and this is the integer part. For integer part, this is 0 1 1 1 1 1 integer part, and this is the rightmost 8-bit for fractional part. So minus 64.75 in decimal place decimal. This is the 16-bit sign magnitude fixed point representation. Next example, and the decimal representation of the following 16-bit Q8.8 fixed point binary number. This 1011 and this. And this is the fixed point Q8.8 fixed point representation, binary representation. We want to find the corresponding decimal number. Now, bitwise position of this given 16-bit sign bit Q8.8 fixed point number, this sign bit, this last leftmost bit is 1, and this next 7 bit for integer part, and next 8 bit for the fractional part. We already know this result. The weighted MSB sign bit. Weighted MSB, the 16th bit most significant bit is equal to 1, and it is the position at 15. Here sign bit is 1, most significant bit is 1, and the position is 15 because the first bit 0, this 2 to the power 0, second bit here 1, this is the position 1, so 2 to the power 1, this is the second bit, first bit, and the 16th bit, and this is the 15, position is 15. This is the because starting from 0, 1 to this 15. So position, so most significant bit position is 15, and this 1. Because there are 8 fractional bits, we must shift the binary point. The weight is calculated related to the implied binary point, and the weight of the most significant bit is the minus 2 to the power 15 minus 8. This total position 15, so this 15, and this is the 8 fractional bit, so we move the binary point, the 8, so 15 minus 8. So actually this is the minus 2 to the power 7, so minus 128. This is the weight of the corresponding sign bit 1. This is the weight, minus 128. If in sign bit is 1, if sign bit is 1, then for 16 bit Q8.8 16 bit, if sign bit is 1, then corresponding weight is minus 128. Remember this result, 16 bit Q8.8 fixed point number presentation, when the sign bit most significant bit is 1 and the corresponding weight is minus 128, and this is the method to find the weight. Note that if the most significant bit is 0, that is positive number, we don't need to calculate the corresponding weight because the contributes 0 to the total value. Next, for integer part, this next 7 bit from 15 to 9 bit, actually this is the 15 to 9 bit, this 0 1 1 1 1 1 1, this is the integer part. For this integer part, this bit count 15 to 9, this part, this integer part, so starting from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 6, and this is the 1 1 1 1 1 0, so 1 1 1 1 1 0 multiplied by weight and corresponding integer part, and we get result 63. So for this integer part, we get the decimal form is 63. Next, for the fractional part, from 8 to first bit, because this is the integer, the fractional part, this last 8 bit, this 0 1 0 0 0 0. So for this part, 0 1 0 0 0, from 8th bit to first bit, this, so this is the fractional part, so this corresponding weight is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and so on, 2 to the power minus 8, and this is the corresponding 0, corresponding 1, this place is 1, and the corresponding this, so we get 2 into 2 to the power minus 2, so get 0.25 in decimal form. So adding all these, this is the corresponding weight of the sign bit plus the corresponding, this is the integer part 63 and corresponding the fractional part, so we get minus 64.75 in decimal representation of the corresponding fixed point 16-bit Q 8.8 fixed point binary number, and the corresponding decimal number is this. Next question, what do you mean by floating point representation? Floating point representation is a method used to represent real numbers in a way that can support a wide range of values. It is the machine equivalent of scientific notation expressed in base 2 because this is binary form. And general mathematical form, the corresponding value is minus 1 to the power s into m into 2 to the power e, because it is expressed in binary form, 2 to the power base 2, 2 to the power e. And this exponential, this mantissa, and this the sine 2 to the power s, and normalized form, and this normalized form is this for this m 1.f. This is the normalized or standardized form is this for this, and this 2 to the power e expressed by 2 to the power e minus b, b for bias and e for exponent, e minus b. This is the e. E is the biased exponent, and e is the actual exponent, and b is the bias. So memory layout, this is the sine bit, this s is 1 bit, bias exponent e equal to e plus b, this is 8 bit, and fraction part is a 23 bit. Sine bit is 0 for positive, 1 for negative, and mantissa part 23 bits. This is the explicitly stored with one implicit leading bit, because this 1 point something, actually this f means this total number is m, so m is expressed as 1 point f into 2 to the power something, so this one is the 1 point, this is the normalized form, and providing 24 bits of total precision. This is the 23 bits for fraction, 8 bit for biased exponent, and sine bit for 1. So total 20 total providing this the this is the 23 bits and 0 sine bit. So this is the 8 bit. (23 plus 8), and this is the 31 plus 32 bits, total 32 bits. Biased exponent, this e equal to e plus b for 8 means n bits exponent, for exponent bit 8 bits, so bias exponent b equal to 2 to the power n minus 1 minus 1, 2 to the power n minus 1, n is 8, so 2 to the power this is 127, this bias is b is 127. And IEEE 754 standard structure, most modern computers follows this IEEE 754 standard. This is the Institute of Electrical and Electronics Engineers. The bits are partitioned as follows. Normally we used 32 single bit. This is the first 31 bit, leftmost bit is 1, and next 8 bit 23 is exponent bit, and mantissa bit is 23. Normally we use this single precision, that is the 32 bit floating point representation. What are the main benefits of representing numbers using floating point arithmetic? Versatility, one format fits for all scale, huge to teeny, very large to very small, and flexibility, it automatically adjusts the scale of the number as calculations continue. Efficiency, most modern CPU have a dedicated floating point unit FPU that makes this complex calculation much faster than the manual software based math. Precision focuses accuracy on the significant digits. Find the floating point representation of minus 6.5 to the base 10. First we convert this decimal to binary. Already we have discussed to convert this process. Next, normalize this binary. Normalize means this the binary point is here 110.1. So move this binary point to such a way that this 1.101, then this into 2 to the power 2. So this can be written as minus 1.101 into 2 to the power 2, because this point move towards left 2 places. So into 2 to the power 2. This is the normalized form. And this is the 1 point f. This is the f. So f is here 101. F is here 101. And this one is implicit. And the sign bit is minus. So for minus, sign bit is 1. Sign bit is 1. And mantissa small f is 101. And actual exponent, this capital is 2. This power 2. This is the power. This 2. Next, calculate biased exponent E, small e. So E equal to, already have discussed, E plus B. This is the single precision, 32 bits. This bias is to 127 and the actual exponent is 2. So biased exponent is 129. Next, we convert this 129 to the base 10 to binary form. This is the 1, 0, 0, 0, 0, 1. So final 32-bit representation, sign bit 1 because this negative number, biased exponent, this biased exponent is this in binary form, this biased exponent, and the fraction part actually f. F is here, this only 101, this fractional part is this, not this integer. This integer 1 is implicit. So we actually put here 101. So put here 101 and the other places filled by zeros. So actually this is the form, is single precision 32-bit floating point representation, binary representation of this decimal number minus 6.5 to the base 10. What is single precision floating point representation of 0.7425? This is the positive number. So sign bit is 0. Now we convert this 0.7425 to the base 10. Binary form is this, and it is going on. It is dot 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 dot. So we round up this up to the 23 or 22 4 places. To normalize the binary number, shift the binary point so only one non-zero digit is to the left. So this the 0.1000, this. So shift the binary point only the, so that only one non-zero digit is to the left. So this is the 1 point something. So this is the 1 point, this is this dot 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 into 2 to the power minus 1. This binary point shifted to one place, right, to the right. So this is 2 to the power minus 2. So this mantissa part, floating point is this, from this 0.011 to this, and this one is implicit. To identify the mantissa consists of the bits to the right of the binary point. So binary point right in the normalized form padded to 23 bits. So here this continue to this, and this if we express this decimal in binary form, then we get continue to this. Now this 24th bit, 23 bit padded to 23 bit, the 24th bit is fractional part is 1. It followed by a more non-zero bit, because the 24th bit is 1, and followed by more non-zero bit, and then we round up to the adding 1 to the 23 bit. So 23 mantissa is given by this. This 4 bit, 448, 412, 416, 420 plus 420, 4 up to this position 24 bit. So 24 bit, this 0, 23 bits is 23rd bit is 0 and 24th bit is 1, and next we get 1 1 non-zero bits. So this 24th bit fractional part is 1, it followed by more non-zero bits. Therefore, this is the round up by the binary rule for this. So this place is 1. Adding this 1, so adding in this place is adding 1. So 1 plus 1, this 0 and this 1. So up to 23 bit. So 1 plus 1 0. This 0 plus 1 is 1 and this 1. So up to last three places 0 1 1. We discard this 1 bold 1. So add to this place 1, this underscore value, this 1. So 0 plus 1 1 1 0. Discard this place. Add 1, round it up. To calculate the biased exponent E, actual exponent E equal to minus 1, because we get 2 to the power minus 1. So actual exponent capital E is minus 1 as 8-bit exponent for single precision, because here the bias exponent 8-bit. So for the exponent 8-bit exponent single precision, so bias B is 2 to the power n minus 1 minus 1. So 2 to the power 8 minus 1 minus 1, actually 127. This is the biased B. So biased exponent equal to E plus B. This E is minus 1 plus 127, that is 126. So 126, convert this biased exponent in 8-bit binary form. This is the 0 1 1 1 1 1 1 0. Hence, this number in decimal is converted to IEEE 754 single precision floating point format 32 bit. This single sign bit is 0. This is the positive number. Bias exponent, this 8 bit. Already have found this bias exponent is this, and Mantissa part, this the Mantissa part is this. Mantissa part is this. So actually answer is this. This is the floating point single precision 32-bit representation of this decimal number. The round up rule, to round to binary number n bits after the radix point, this binary point, examine the bits followed the nth place. Round down if the first bit after the nth place is 0, discard it and all subsequent bits. Round up if the first bit after the nth place is 1 and any followed bit also 1, add 1 to the nth bit. And try breaking, ties to even if the first bit after the nth place is 1 and all following bits are 0, check the nth bit, the last bit to keep. Number 1, if nth bit is 0, even, round to even, truncated, and if nth bit is 1, odd, round up, add 1 to the nth bit to make it even. Consider the following example. And this is the, we want to this binary number rounding to 2 bit. So we want rounding to 2 bits. So we want 10.10. This is the binary point 10. And this is the third bit here 0. And next bit is 0, is the next bit bold digit, this 0. The action round down, truncated, and this, because this place, this is the nth place. We actually want to rounding to 2 bit, and this place is 0. So just truncated this. So up to 2 bit is 10, because this 0 here, n plus 1th place is 0 here. Bit is 0 here. Next, for this number, we want to 2 bit. This place is 1, and followed by a at least one non-zero bit. This one. So we add 1 to this place. So 1, 0 plus 1, 1 and 1. So this is 0.11. Next, by this rule, by this rounding up, bit after the nth place is 1 and any followed bit also 1, add 1 to the nth bit. Next, tie. This we want to rounding to 2-bit, this 1 and followed by zeros. So we simply truncated round to even, this 1 0 1 0. But here is 1, but follows by zeros. This is the, if the nth bit is 0, even rounded to even truncated. The nth bit, the last bit, keep the following bits are 0. Nth place is 1 and all following bits are 0. Nth bit is 1 and last following bits are 0. So just truncated this 1 0, and this is the rounded to even. This 0 is even. Next, rounding to 2-bit, here 1 and all zeros, but here this place is 1, this next bit is 1, rounded to even by adding 1 with second bit 1. So add this 1 by this rule. If nth bit is 1 odd, round up, add to the nth bit to make it even. If the first bit after the nth place is 1 and all follows bits are 0, after the nth bit, here nth bit is 1, after the nth bit is 1 and follows 0. So this round to even by adding 1. So add 1 with this 1. 1 plus 1, 0. Carry 1. 1 plus 1, 0. 1 plus 1, 0. Carry 1. So 1.00 by this rule. Next question, binary floating point to decimal conversion. Convert the following single precision floating point binary number to decimal number. And this is the 32-bit single precision floating point IEEE 754. We want to convert to a decimal number. Here the leftmost bit is 0. So obviously this is the positive number. And biased exponent E, this 8-bit, so 0 1 1 1 1 1 0. So up to from this place to this place is biased exponent. So biased exponent is this. Convert this biased exponent part in decimal part 126 to the base 10, and the rest part 23 bits 4 4 4 4 4 3. So these 23 bits is mantis or floating fraction. Mantis or fraction. Actual exponent E calculated by this biased B is 127. So actual exponent capital E, we know the formula, biased exponent equal to actual exponent plus B. So the actual exponent E minus B, that is the 126 minus 127. This is the minus 1. This is the minus 1. Next, for fraction part, this is mantissa part, where the 23 bits is this. Adding to implicit leading one, because we delete this leading one, this 1 point this. So now we add this leading one, 1 point m. M is this fraction part. So 1 plus 0 for this 0 0, this fraction part, so multiplied by 2 to the power minus 1. Next 1 into 2 to the power minus 2, so this and this, and last 23, last 23 is 1 into 23 this, last one is this 1 into 23, and 0 into 2 to the power minus 21. So 1 point m is this in decimal form. So final value is minus 1 to the power s. Here s is 0. So minus 1 to the power 0 is 1. This 1. 1 point m is this, and e to the 2 to the power e. E is the minus 1 here, actual exponent. So 2 to the power e. So we get this rounding to 0.7425 in decimal. What are the differences between fixed point and floating point representation? In the fixed point, a point position stays in a static predefined location, and floating point position floats or shift based on the exponent. And range, for fixed point range is very narrow, limited, whereas floating point range is extremely wide, dynamic range. Precision, for fixed point, constant absolute error, same gap between all numbers. And for floating point, constant relative error, gap grows as a number get larger. However, for fixed point, simple circuit, faster and low cost processors. For floating point requires a dedicated floating point unit, not low cost processor. A representation for fixed point similar to standard integer qm.n or q8.8. For floating point similar to scientific notation m into 2 to the power e. Primary use, fixed point, digital signal processing, embedded system, etc. And floating point,